when the lights of the car are switched on, an ammeter in series with them reads 10 amps, and a voltmeter connected across them reads 12 volts. When the electric starting motor is turned on, the ammeter drops to 8 amps and the lights dim somewhat. If the internal resistance of the battery is 0.05 ohms and now the ammeter is negligible, what's the EMF of the battery and the current through the starting motor when the lights are turned on? All right, so a quick note on this one. We've got a voltage drop across that internal resistance, but we can do a quick couple calculations. One is we know that during this first portion, the current through this circuit is 10 amps going this way. Why? Because we know there's 10 amps going through this voltmeter. The starting motor is not turned on, so we can actually figure out what the voltage drop is across this internal resistance, and that's going to be 0.5 volts. But we know that this voltmeter here is right now reading 12 volts, so whatever the EMF is here, minus the voltage drop of 0.5 volts, is still got to read 12 volt difference between the two terminals. That means, by logic, the EMF of the battery has to be 12.5 volts. With the 0.5 volt drop across the internal resistance would give us a terminal voltage of the 12 volts that we're expecting. Now this next part gets a little bit more interesting. Suddenly the starting motor is turned on, and things get just a little bit more exciting. The first thing I want to figure out before we do anything else is what the resistance of the lights are before we turn on the starting motor. We'll need that to be able to calculate much else in this circuit. We know Ohm's law, I equals V over R, current equals voltage over resistance. Rearranging that, we can solve the resistance of the light bulbs. Why? We know they were seeing 12 volts before the starting motor was turned on, and we know the current through them was 10 amps, meaning the resistance of our lights has to be 1.2 ohms. We can also use that information along with the fact that the ammeter now reads 8 amps when the starting motor is turned on, to figure out what the new voltage is. In other words, what's the terminal voltage? Well, again, remember voltage is equal to current times resistance. In this case, we know that the voltmeter would actually be reading 9.6 volts. And you might say, whoa, wait a second, how do I know that? In this case, 9.6 volts across a resistance of 1.2 ohms will produce the 8 amps of current that we're actually observing. Now, we don't actually need this number directly, but we're going to use it because we can actually figure out what the voltage drop is across this internal resistance. And based on that, we can actually figure out what the current is coming out of the battery. Let me show you. We know the voltage drop has to equal IR. In this case, what's the voltage drop? Well, we know the source of EMF, the battery itself, is 12.5. And we know that the internal resistance, R, is 0.05. Based on that, we can tell, or actually know, that there are 58 amps flowing through this internal resistance. Now, what happens on the outside? Well, voltmeters have almost infinite resistance, so none of it's going through there. So our 58 amps are coming up here. Part of it's going through the starting motor, and part of it's going through the lights. So we know 58 amps are coming out of the battery. Because of the amp meter, we know that 8 amps at this instant are going up to the lights. And yes, also flowing back this way is 8 amps. Meaning, logically, the amount of current going through the starting motor must be 50 amps. So on this junction over here, 50 amps heading this way. So it splits up nicely. And those are your two answers. Good luck.